Hello everyone and welcome back to Manic Analytics. I'm very pleased to have you back once again. In today's video, we are going to see how we will be applying the principal component analysis. We are going to solve a problem using the principal component analysis. In the previous video, we saw how we can use the principal component analysis. We saw the different ways you can use while determining the variance, and we also saw how we can plot the script plot to determine uh, the the number of principal components that you will use depending on the problem that you're solving. So we are going to use the ideas that we learned from our last video. Now we are going to use that to try to solve this problem. Before we get started, I would like to ask for assistance. Please subscribe to this YouTube channel. We're welcoming you to this wonderful community. Hit that the notification bell so that you never miss any of our video updates. Once again, thank you for your time, and let's get started. So as I had said, we are going to be using the PCA to try to solve a problem. So this is the problem that we will be trying to solve. So I've already detailed. So in this case, we are going to the case or the topic for this problem is all about enhancing a human activity recognition, and we are going to seek the help of the principal component analysis. So what's the background of what you're going to be solving today? So the Human Activity Recognition HAR database captures the daily activities of 30 participants through recordings made by waist-mounted smartphones with embedded inertial sensors. So the objective is to classify activities into either of the 6 categories, which include walking, walking upstairs, walking downstairs, sitting, standing, as well as laying. So what is the challenge as to why we are going to be using the principal component analysis? Now, with the data set containing multiple features for inertial sensors, we face a high dimensional space that may pose challenges for modeling and possibly visualization. So for this case, we aim to enhance the analysis by applying the principal component analysis that will enable us to reduce the dimensionality of the feature space while preserving the essential information in our dataset. So that's the problem that we're going to be tackling in this problem. So at least by now, I think you now have the context or what we are trying to beat, or the goal that we are trying to achieve. So after that, then let's get started and see how we can solve this problem. So as usual, I will start by importing the necessary libraries. So I'm going to import the libraries. The libraries. So put numpy as NP. So we are going to import numpy. So import the pandas PD, and for visualization, I'll use matplotlib. Matplotlib pyplots. Okay, so those are the libraries. Then after this, we move on to importing our dataset. So this is the dataset. With the head method, again, we're just printing the first five rows of our data frame. So with this data frame, you can see these are the first 5 rows, and you can see we have a total of 563 columns. So you can see the dimensionality space is quite huge. So the data summary, we are going to use info. You can see that we have 2947 entries. We have 563 columns. So you can see this is quite a huge number. Okay, so from all these columns, we have 561 columns that are floats. One column that is the data type is are integers, and one are objects. Okay, so again, we are going to loop through all these columns and check for the missing values, just similar as to what we did earlier or in the previous video. So we are going to loop through each column and check for missing values. So we use the for loop. So for column in df.column, so for columns in our data frame, and then we're going to check for the missing values. So if a column is null, then sum. So is null is a function that is used to check if you have missing values in the columns, then we're just going to sum. So if you have 6 values, or if you're missing six rows in a single column, then we're just going to sum that number. We're going to sum the number of the missing values in that particular column, and it will return a result. That result will be in the column missing values. Then we are using another if block, so like another loop inside the for loop. So if the missing values that we obtained is greater than 0, then we are going to print this statement. And if you are going to print this statement, it means that we are going to break. We are going to break. I think we're going to break out from this loop. Then that means we won't be executing this block of code. But if we don't have missing values, this will be executed and this will be executed. Okay. So after we run this, you can see that the data frame has no missing values. That means we didn't utilize the break statement here because we don't have missing values in our column, in our data frame. Sorry. Then that's why we just printed this. So I will check for duplicates. Checking for. So these are just some of the common ways of checking for or cleaning your data. So I'm going to check for duplicates. So duplicated. And I'll use skip false. Then and just sum again. When we execute this 0, then we don't have missing values. We don't have missing values. Earlier on, from the data summary, we saw that we have a column that contains data type is object. So that means possibly it contains strings. So we are going to encode that column. I think it's the column activity. I think this is our target. This is our target variable. So we are going to encode that. I'll use the label encoder, which is the most simple of the encoding processes. So I'm going to encode. So for label encoding, I'll start by importing the libraries for that. So from sklearn.preprocessing, sklearn.preprocessing, we're going to import the label encoder. So Then after this, I will create a list of columns to encode. So unfortunately or fortunately for this, we only have one column. So the column activity. Okay. Then to avoid interfering with the values from the other columns, I will just create a copy of the original data frame. So let's say we call it data. So df.columns. I'll use the copy function, sorry. Then after we are done with this, then we can then initialize the label order. Then here, so first create an empty kind of list for that. So then for encoding, I'll use a for loop. So for call columns. Then here label encoders. Then we recall our label encoder. We create a function for that. Just here. That we can then do the encoding parts. So label encoders. So from here we can then now use the fit transform. The fit transform. Okay. After we have done with this, we can then, so remember we created a copy of our data frame. So I want to retest that process back. So from data.copy, so I will copy back into our original data frame. So I'm just after we create earlier on, remember we created a copy of the original data frame. So then here I'm just now after conducting the label encoding, we're just now going back to our original data frame df. So for me, I like using df. So when I execute this again, I'm getting an error. Columns supposed to be, you have spelling somewhere. Columns supposed to be columns. So you can see now the column activity. You can see now we have now encoded, we have substituted the categorical values in the column activity and we have assigned them a numeric values. Remember that the algorithms that most of these algorithms that we are using, they prefer numeric input. Okay, then we can check for the class labels. So for the class labels, you can see we have a total of 6 classes. So 0, I think 1, 2, 3, 4, 5, 6. We have a total of 6. 0, 1, 2. So you can see that they are of different count. Okay. For the class labels, from the look of things, they're not hugely. We cannot see a huge imbalance in the count of these labels. So maybe we want apply the methods of reducing these class imbalances. Okay. So after this, we can then import the necessary libraries. So since this is a classification, this is a multi-class classification problem. Before we get that, let's first import the necessary libraries. So I will import the train test split, the standard scalar. We will use the logistic regression model algorithm. So I'll also import that. We'll also use, maybe try out the random forest. I'll also import that. And also the accuracy, the methods to check for accuracy. You can, so this is the train test split, the standard scalar, the PCA, then the logistic regression, because we are using that. We can also import the classification metrics. Since we will be using the random forest, we can also import the expertise random forest. We'll use either. Okay, so these are the libraries and the modules, the way you okay. So after this, we can then first split the data into the features as well as the target variable. So we are going to define the features and target variable. So here x will be df dot drop activity. So this axis equals 1. So this is then our target variable. So again, df activity supposed to be activity. So after defining our features on the target variable, we then move on to splitting our data. Split to training and testing. So here again, the x train, x test, y train, then y test, x train, then use the train test split function. So train test split, the train test split, so x then y. Then we specify our test size. So test size, I will use 0.25. Then random state, let's say 42. Okay. So after splitting our data into the training and the testing set, you can see x test, y train, y test. Yeah, everything is okay. Then we move on to now to applying the standard scalar. So scalar, standard scalar. Then after this, going to x-train scale. X-train scaled. So scalar dot fit transform. We want to transform the training data as well as the testing data. X scaled. So again, scalar, we're just going to fit the x test. Okay. Here, scalar dot transform. Okay, so after applying the scalar, let's train our model. Train before applying PCA. Let's do a training before applying the principal component to see if how our training will look like, or how our model will perform or behave. So let's first use the logistic regression. So I'll create the logistic regression model. So we can say logistic regression. Logistic regression. Then I'll specify max. Then after this, we can then fit the model to training data. So for fitting again, so the LG model dot fits. So here we're going to fit the X-train model, X-train scaled, as the Y-train data. Then after this, predictions, make predictions. The predictions, I'll say Y-pred logistic regression. Then you can say LG model dot predict. So we're going to predict the X test scale. So after making the predictions, we can then print out the classification report. So the classification report. Classification report, that is will be between our Y test, the true value against what was predicted. So we can run this. So this is the model is performing quite well. There are no we're getting good precision values, the recall, the F1 score. We are getting good values for this. But let's create a problem for ourselves. So it's performing quite well, but let's see now after we use. So this is the training before applying the PCA. So if you're going to be using the principal component analysis, so how are you going to do that? So again, let's do that. So we're going to see the results after applying the principal component analysis. After using PCA, let's similar to what we did in the first video. So in this case, I'm going to choose. So you're going to choose the number of components based on the script plot or explain variance. But I'm going to set that we maintain 95% variance. Then after that, I'm going to fit and transform on the X-train scaled data. So remember, after performing the scaling, our training data, X-train scale. So that's what we're going to be fitting and transforming using the PCA. And then after that, we're also again going to transform the test set, again using the PCA transformation. So this is how you this is how you can use the principal component analysis. Now, so this the PCA comes after you have done your after you have defined your features on the target variables, and then you split your training into training and the testing data, because we then after scaling, that's when you apply your PCA. Okay, so we are applying this only on the okay. So after this, then we can then apply the logistic regression model to see. So after applying our PCA, then we can then move to the logistic regression. So this is the logistic regression model. Again, after this, you train the model on the PCA transform training data. Okay, so the X train PCA and the Y train. Then after this, you can then make predictions on the PCA transform test data. Okay, so I create logistic regression model. Then we make predictions on that, on the test data. Then after that, we can now do a model evaluation, see what we are getting. So after executing this, this is the model that we are getting. You can see after using the principal component analysis. So basically, this one was when we were using every data point. So you can see we are getting a slightly higher metric values for the precision recall as well as the F1 score. But after applying the principal component, we can see that we are getting slightly lower values for the precision and the recall. So basically, this is because, remember, we are losing some values, we are losing some data when we apply the PCA. Okay, so for example, let's say if we change this, let's say we only reduce this data to only 25 principal components, and let's see if our will improve on that. So when we execute this again, we can see again there is a slight decrease. Okay, so let's do 15 and see. When we decrease that to 15, then you can see we are getting a slightly decrease in that. This is just because we are losing some data. Okay, but now I think you can see how we can apply the principal component analysis. So okay, so let's try this with a different algorithm. Let's use the random forest. So with the random forest, we can also do the before and after. So let's do before, applying the PCA. You can do the before and after and see how the model is performing. So we created an instance of the random forest classifier. Then we fit the X train as well as the Y train. Supposed to be X test scaled. Then after this, we can see the classification report for this model. The random forest, you can see it's taking quite some time. So we'll just wait for the model to train. So for the random forest classifier, when you compare this before and after, so we have an accuracy of about 98%. The logistic regression, we had an accuracy of about 99%, so it's quite lesser than that of the logistic regression. And when it comes to good precision for class 0, 97, 95, 99, 99. This one was 1, 97, 97, 1, 1. Okay, so logistic regression is performing quite better than the random forest. So after this, let's apply now the principal component. This, so we can say after application of PCA. Let's see now how our model will perform. So this initialize, this is supposed to be the random forest classifier. Then we train using the X10 PCA. Okay, X-test is supposed to be X-test, X10, X-test PCA. Supposed to be X-test. Okay, that's okay. And so when we compare, so after applying the PCA, these are the results from that. Again, you can see now with the decreased information, or the PCA again. Remember, let's try 90. Supposed to be. Let's try when we maintain, or let's just copy this and use it before here. So we can just create a new cell, paste this, so that when we execute this cell from here. So again, let's say we can just rename this to X10 PCA1 and X-test PCA1, so that we won't. Okay. Then here for X10 PCA supposed to 1, X-test PCA1. Okay, so let's execute this and this again. So when maintaining 95% of the variance, let's see what metrics we are getting. You can see we are getting they're relatively close, but slightly less, I think so. Slightly less than what we got earlier. 98% accuracy. You can see this one is 95% accuracy. Let's say for class 2 and 3, 95, 92, 95, 2 and 3, 95, 99. So with the decrease of data, then you can see that we are getting slightly lower values for that. Okay, and let's say if you're only maintaining 10, only keep the 10 first, the 10 principal components, and see what values, what data we can get. So while maintaining that, you can see that we have a decrease again in the accuracy, in the overall accuracy of the model. Okay, so that's it again. So that's it for this video. Once again, we have now try to apply the principal component analysis given a problem. So you can see with this problem that we are solving, it had about 563 entries. Okay, so and we applied the principal component so that we can try to reduce that dimensional space, and we apply that. Maybe let's see. Is something that we missed. Let's see, after applying this, let's see the shape. Let's see, after applying you can see this one, we reduced that to 15, okay? 15 is quite small. After applying the principal component analysis, after we determine the n components, we said when we use the 95% variance, you can see that we reduce that number to about only 15 features. Let's see, when we did the extend test split, let's see how what is the shape of this shape. When you execute this, you can see when you did the split of the when you did the train test split, you can see that, for example, our x-train, when you find the shape of that, you can see we have a total of 562 columns. But when we applied the principal component now on our training data, here, we can see that after applying the principal component and determining the number of components now on your data, you can see that you only had a total of 15 columns. So you can see that massive decrease in the feature space. So that's why with that decrease, we can see that we are increasing maybe the speed of training. So you can see that our models are, while training, you can see that we are a little bit fast in terms of training. So basically, this is just an example to illustrate or to show you how you can apply the principal component analysis. So I think you have seen how we can apply the principal component to maybe reduce that dimensionality of our data and make it easy to analyze, maybe decrease the training speed. So in some examples, for example, you can be having, for example, if you are doing analysis or trying to build models to classify pictures or photos, so you sometimes can even have feature space, or the dimensionality space could be even be thousands, 100,000, millions. Okay, so when dealing with that type of data, then then you might need to use now the principal component analysis to try to squeeze that dimensionality into a shape that is easy to model with. So again, that's how you can apply that now while trying to solve a problem. So that's it for today. Once again, before we sign off, please consider subscribing to our YouTube channel. Hit that notification bell so that you never miss any of our video updates. Once again, I'm very grateful for your time, and until next time, see you.